In the previous video, we discussed about complex numbers, and we introduced the highly important identity that e to the I theta is cosine theta plus I sine theta. The importance of this equation will be discussed and will make sense in this video when we discuss about Joseph Fourier. In 1822, Joseph Fourier, who was a very famous and influential mathematician and physicist in his time, was studying the properties of heat and wanted to develop a mathematical theory governing all of heat transfer. So he published a paper called The Analytical Theory of Heat, in French, of course, his native language, and in it there was one problem where he had a thought experiment of two metal rods that were separated, right? And one of the rods was hot at a high temperature and the other rod was at a cold temperature, right? Let's call this T sub H, or rather, we'll use his statements where we have U sub H and we have U sub C. So hot temperature and cold temperature. And they are apart at time is less than 0, right? At time is equal to 0, these two are brought together and they touch, right? And now when they touch, what we have is we have a direct interface. And he wanted to know how the heat would transfer and dissipate or distribute itself over the rod over time. Now, if we were to plot this on a graph, what we would have is we would have space, right? And the rod has a length of, let's say, L. And here we would have U of time and X, right? But we're only plotting it against X, right? Now, here we have the temperature of this rod, but here, let's say down here, we have the temperature of this rod at U sub C. Here we have U sub H. Now, there is a steep change between these two. It's a step, and there's a discontinuity at this point because here there is no defined temperature, right? And when he was analyzing this situation, this equation popped up where the partial derivative with respect to time of the temperature was equal to some constant times the double partial derivative with respect to time of the temperature. And this differential equation is known as the heat equation. But there is also a case and an equation to be solved in 3 dimensions. In his efforts to solve this equation and to analyze heat, he made 2 brilliant observations. The first brilliant observation was that if you have a periodic function, like let's say we have a function that looks like this. It looks like that. He observed that this could be made up of a fundamental sinusoid. In addition to that, another higher frequency sinusoid, which is a multiple of the frequency of this fundamental sinusoid. And he observed that any periodic function, which is any function which satisfies this equation where t is the period, right? So here would be t, and this is the period for the function to restart, right? This is the equation for periodicity, the condition for periodicity, rather. Any function which satisfies this condition can be represented by the following series, where we have C naught, which is a constant, right, plus the sum from n is equal to 1 to infinity of a sub n cosine of omega nt plus the sum from m is equal to 1 to infinity of b sub m sine omega mt, where omega is equal to 2 pi over the period, right? And this is the fundamental frequency. So this would be 2 pi over this large sine waves frequency, period, sorry. But now, one big question arises when looking at this, is that how do we calculate the coefficient? Well, the C naught coefficient is a height term. And what that means is if we have a standard sinusoid, let's take a standard sine wave, right? And here we have 2 pi, right? And it has a magnitude of 1. So this is sine of t. Well, if we take a derivative over the period of sine of t, with respect to t, what we'll end up with is we have minus cosine of the period plus cosine of 0, right? And after a period, this is the same as 0, because remember, it's a periodic function, and 0 plus the period is just equal to the function at 0. And here, these are the same, it equals 0. And the same holds true for cosine and any other periodic sinusoid, right? But if we add a constant term to this, so instead of just being this, right, it's plus some C naught, right, dt, we will get, this will be 0 and this will be C naught, and it will be t times C naught, so we will get C naught times the period. But we would rather to just get C naught, right? So let's just modify our equation to do 1 over the period, and thus we will end up with just C naught. So here we now have the equation for the, what we will call the DC term, for direct current term. And it is equal to 1 over t over a period times your function of t with respect to t. Now, it is important to note that when integrating over a period, it does not matter what the bounds are. You can go from negative t over 2 to t over 2. You can go from t over 2 to 3t over 2. It really doesn't matter, as long as it's over one period. Okay, but now, what about the sinusoidal terms? Well, in order to talk about those, first, let us talk about a phased sinusoid. So imagine we have a sinusoid of this form. Well, this can represent any sinusoid, right? Because if we wanted this to be cosine, we could just add pi over 2. Expand this, we would get sine of omega t cosine of phi plus cosine omega t times sine of phi. And here, cosine of phi and sine of phi are constants that just depend on the phase shift, and thus we have it that it is a sine of omega t plus b cosine of omega t. Thus, if there are any phased components in our signal, it can just be broken down into two sinusoids. So we do not have to consider phased sinusoids. But now, let's move on to a little example in Desmos. Here in Desmos, we have a sinusoid, which has the expression sine of 2 pi over t n x, where t is a period being 8, and the multiplying factor is 2. So effectively, this sinusoid has a period of 2. And, sorry, not 2, it has a period of 4 and a angular frequency of pi over 2. Let's add another sinusoid, which is the same but has a separate period. And we can ignore this phase shift component, like I said, and I can vary the period of the second one, right? So the period of the second one is changing, but the period of this red, h of x, is always the same. Well, here in purple, I have the product of both the red and the blue sinusoids. And you will see as I change t, it changes shape quite drastically, right? But notice that it is still periodic, right? It is still a sinusoid. Here in block 9, I have an integral, which integrates over a period for this purple sinusoid. And now, if we look at the values of t, you'll see that for most values of t, it is close to or equal to 0. If you'll notice, if we get to 4, it is equal to 1. And if we take a look at the graph, we'll notice that it is purely positive, right? It does not cross the x-axis and turn negative. And the reason for this is that this sinusoid f of x and this h of x are now the same function. They have the same period, they have the same angular frequency and magnitude. So they are just squared. This is essentially just h of x squared or f of x squared. And because it's squared, it is purely positive. There is one thing to note, that if we look at the values of this integral, we'll notice that it's a bit, when we're close to the period, right, the integral is still around 1. It's not that close to 0. It kind of tapers off the further away we go from the period. And if I increase this period to say like 100t, right? So we're integrating over a very large period. And we look at it, we'll see that this problem is much less pronounced. And the reason for this is that because we're only integrating over one period, there is some uncertainty. We are less certain about the period for our sinusoid. And this is because when we're integrating over a shorter period, there's more uncertainty in what the period of the sinusoid actually is, because we don't have that big of a sample, right? We're not integrating over that much. For the most part, it's good enough to just integrate over one period. Going back, now we have discussed that if we take an integral over a period of two sinusoids with different frequencies, I'll just do it this way and I'll put a theta t dt, right? This will equal 0. At least it should equal 0. Especially if we increase this to be infinite. It will definitely become 0. All right. But if they are exactly equal, what we end up having is we have an integral of this sinusoid squared. So over a period, what we'll end up with is this can be rewritten by the trigonometric half-angle identity. It can be written as 1 minus cosine of 2 omega t over 2 dt. And now this is a sinusoid, so this term will just go to 0, and we have half times the integral, so it's t. Oh, this is supposed to be t, right? So it's half times t. But we want this to equal 1, so let's just modify our original integral to be the reciprocal of this, so it will be 2 over t. So now we have 2 over t, and this should be 1. All right, and this is the same thing for cosine. And thus, we now have our synthesis equation for the coefficients. So we have 2 over t times the integral over a period of the function of t times cosine omega nt dt. And we have b sub m is equal to 2 over t times the integral over a period of f of t sine omega mt dt. And these are the equations for our coefficients. So here we have the constant dc term, and here we have the sinusoidal terms. Now, to carry out these calculations is a bit time consuming, but it shouldn't be too difficult if you're familiar with doing calculus with trigonometric functions, right? And I have prepared an example. Here in front of me, I have a Desmos demonstration for two Fourier series which I have calculated. This f of t is a square wave with a period of 1, and it has a height of 1, right? And this one is a triangle wave. So it has a period of 1, right? So it is equal to t in the interval. So it will have a height of 1, right? But if I increase the period, it will go on to have a height of whatever my period is. The height is dependent on the period, which can be seen here. It can be seen because it depends on the period, whilst our square wave has no dependence on the period. Okay, but looking at our square wave, here we have the integral, and we're going to change the number of terms of the series that we're going to do. So here we're going to have one term in the series. Here we're going to have 2, 3, 4, and as I increase the number of terms, you'll see that it gets closer and closer to the square wave that it is supposed to represent. And it does, except there's these spikes at the edges. And these spikes are called Gibbs phenomenon. And in fact, this was not known about for quite a bit after the discovery of Fourier series, because they had to plot this by hand, and nobody bothered to really put that much detail into plotting the discontinuity. And as it turns out, in order for the sinusoid to reproduce this very steep edge, it has to quickly increase its magnitude, and then it quickly decreases it and levels out again. And it does it at every single discontinuity. And actually there is an equation to know how high it will be depending on the steepness. Let's now look at the other example, which is a a triangular wave. And this triangular wave, you'll notice, has the same Gibbs phenomenon at the discontinuities. And if I increase the period, you'll also see that the height increases just as I said. Because again, the triangular wave is dependent on the period because it is just equal to t. It is just a steady linear ramp for the entire time that it is defined. And thus, it varies with the period. Now that we have discussed the Fourier series and how to calculate the coefficients, let's go back to our original equation and notice for the Fourier series we had the condition that it had to be periodic. However, this function is not periodic, it's aperiodic, right? It is very much just defined in a finite interval. Well, this is Fourier's second brilliant insight. He realized that if you have, let's say, a function that's defined on an interval between, let's call this minus L and let's call this L, and let's prop up a 0 in the middle, right? And let's say that the function is defined in here, and it looks something like this, right? It is defined between 0 to L, and I'm going to call it f of t, or rather, let's change it up and let's call this x of t, right? Now, this x of t very much is only defined on the interval from 0 to L, right? We'll add a discontinuity here because... Okay. Now, if I define a new function, let's call it g of t, right? And say that it is equal to x of t plus x of t plus L, what happens is now we're adding on the function again here, right? The same function and the same discontinuity, right? Except now this is defined on the interval, instead of from 0 to L, it's defined from minus L to L, right? We've extended it, but still this g of t holds the information of our original function. We didn't lose anything. All we have to do is close the integral in which we're looking, the interval in which we're looking in, to the interval of our original function. And in fact, we can continue doing this, and we can continue adding more and more, right? And we can actually continue this ad nauseum, right, to get a g of t which is defined as such, where we have the sum of x of t plus k times L, where k goes from negative infinity to infinity. And now we have a periodic function defined on the entire number line, just as with the condition we had before for our Fourier transform. And now, just through adding together the same aperiodic function, we have turned our aperiodic function into a periodic function. And if we make a Fourier series of this, all we're going to get is a Fourier series of the periodic function. And if we just want to have information about the original function, all we have to do is only look on the interval from 0 to L. Nothing has changed. And that is how you are able to use the Fourier series to help solve this equation. But moving on, we're talking about what is known as Euler's formula, right? Which links complex exponentials to a sum of sinusoids in the complex plane, right? Well, the reason we talked about that is here we have sinusoids. And in fact, if we take this and take C naught is equal to, let's change them to K, right? And it doesn't really matter if these are two separate, right? We can just pull them into one and do them all at once, right? So let's do that. So we have A sub K times, and let's expand out cosine of omega nt to get e to the I omega nt plus e to the minus I omega nt divided by 2, right, plus b sub k, and let's expand out sine, which is e to the I omega nt minus e to the minus I omega nt over 2I. And this, right, we can work with this. First of all, let's notice we can just factor out this 2, right? We can factor it out. So we can take these, we can take these and we can move them here. Secondly, we can notice that we can group these. We can group these, right? And we can group these. And finally, let's notice that we have an I in the denominator. Well, this I in the denominator, right? If we have 1 over I, we can multiply by I over I, which is just 1, right? And we get I squared, so I over I squared. And this I squared, by definition, is minus 1. So we have minus I. So 1 over I is just equal to minus I. All right, so now let's go on to the next step. So we have C naught plus the sum from k is equal to 1 to infinity of a sub k. Oh, forgot to put the half. Okay, a sub k minus I b sub k e to the I omega nt. Right, now let's separate them. So let's go plus 1/2 times the sum from k is equal to 1 to infinity of, now let's take a sub k and then minus minus plus I b sub k e to the minus I omega nt. Right, now, first of all, let us define a sub k minus I b sub k equal to c sub k. Oh, and let's put in the half. Right, and by doing this, we also have that this is the complex conjugate, which just means that we are flipping the sign of the imaginary part. We can further simplify this equation now to just be sum of k is equal to 1 to infinity of c sub k e to the I omega nt. And notice that this is also, right, it's also a complex conjugate, right? But it's also oh, forgot to make these k. Right? It's also just minus k, and this c sub k is just, we can say that it is just minus k. And what we end up with is that we have the integral of, let's just move the minuses onto the boundaries, right? So then we get c sub k e to the I omega kt. So these two are the same, except this is minus, right? This is over the minus axis. This is over the positive axis. And this is, well, if we set k equal to 0 on either of them, we have, this will just become 1 and we'll just have c sub 0. So we can absorb them all into one term, being the integral from minus infinity to infinity of c sub k of I omega kt. And this sum is our new complex Fourier series. And you can clearly see the benefits of using complex numbers, because we had this long equation that was quite difficult to work with, and now we have this small equation that even takes much less time to write. Well, now we have a big question of how do we calculate c sub k, well, let's try the same logic as before, where we have two not sinusoids, but complex exponentials. So we have xt, and then we have I omega t. This x of t and this omega of t, if they are not equal, this integral has quite a small value, just as the case with these integrals. However, if x is equal to minus omega, right, in this event, what we get is the integral of 0 to t, and these two will just cancel out to be 1. So dt will just get t. But we would just want it to be 1 again, so we'll modify this to be 1 over t again. And we will end up with 1. However, what this would be is it would be scanning so that when I get a frequency, it would map to the opposite frequency. It would map to a negative frequency rather than a positive frequency. So I'm just gonna flip the sign of this term. And we would end up with c sub k is equal to 1 over t times the integral over a period of f of t e to the minus I omega k t dt. All right. And now we have the complex coefficient for the complex Fourier series. And because of the way that we have defined c sub k, right, we can even get out the normal coefficients, right? We still have to carry out this integral, right? But instead of having to carry out these two lengthy integrals, right, all we have to do is, if we want a sub n and b sub m, all we have to do is take, well, we have it that c sub k is equal to half a sub k plus minus I b sub k. So now what we have is we can just take c sub k and we'll take the conjugate and add it to the standard one. And what we would have is we would have minus and plus cancel out. And we would have 2 times half a sub k, so this would just be a sub n. And now b sub k is the same thing, except we, instead of adding, what we do is we take the conjugate and then we subtract this one. However, now we're gonna have I, so we have to take this and divide by I, or rather, we multiply by minus I. And now, from that, we only have to carry out 2 integrals. This one and the very simple one of just integrating over a period. If we look at our complex Fourier series, right, specifically, let's look at the coefficient equation. And just as with before, let's write it out. And the thing is, this is only taking it where omega is an integer multiple of a fundamental angular frequency. So what if we just take it to be a variable omega, so c of omega? And in order to do this, we can't just integrate over a period, right? We can get rid of this because we don't care about the scaling as much anymore. But now let's integrate over a larger and larger period. In fact, let's just integrate over all time. And now, integrating over all time, And changing this out, now what we have, all right, is if we have a function here, t, and we have f of t, and would plot it, let's say it looks something like this, I don't know. And then we also plot another graph, which is c of omega with respect to omega. Well, what we'd find is that this would be very small for any value in which this does not have the same frequency. So this will scan and look for the frequency components, and what we'll end up with is we'll probably have like peaks like this, right, in our signal, where, or even would have more distinct peaks rather. And now a question arises of, okay, well, what's going on? Well, what's essentially happened now is, you see, we have taken a function in the time domain and we've turned it into a function in the frequency domain, right? And these, it's just been transformed into the other. So we've taken a function in the time domain and taken its equivalent in the frequency domain, or its analogy in the frequency domain. And what's actually happening here is, if we go on the complex plane, and let's imagine that our signal has frequency vectors like this, and like this, and like this, like this, and maybe like a really big one here, and we have our vector here. What we're gonna do is we are going to scan in this direction. And in blue, I am going to plot what the value of the product here of the integral will be. Well, we're going to have a small, very, very small value. It's going to rise a bit, and then it's going to rise a lot, right? And then fall, and then a bit, and then rise a lot, fall, rise again, and would get a bunch of spikes like that, and would keep going and faster and faster and faster and faster, right? Because instead of varying t, these would move along with t. We're varying omega, right? So we're just scanning along, and we're essentially holding our function stationary and just scanning over and multiplying and eliciting the information of where the frequencies are. And this would plot to look something like this. So here we'd have omega, and let's call this f of omega, right? This would plot to look something like this, where it would be a small one, and then it would be a big one, right? Sorry, it would be a small one, and then it would be a big one, and then it would be another small one, and then a big one. And this is absolutely pivotal to so many fields in modern mathematics, physics, computers, audio engineering, signal processing, in astronomy, in anything to do with waves and information. This Fourier transform is an absolutely core concept. And to go even deeper, in physics we learned that the energy of a wave is proportional to the square of its amplitude. And because here we have the amplitude of the frequencies, what we essentially have is the energy spread, right? So we have the energy of our function at a specific omega. What this f of omega, what the Fourier transform tells us, is it allows us to see the spread of energy over the frequencies. And now, with that in mind, Let's move on to a distribution called the Dirac Delta function. The Dirac Delta function is denoted by this Greek delta, and it's normally with respect to x, because what Dirac was doing when he came up with this distribution or function, right, was that he was studying charges, so specifically electrons, and he had point charges, and he wanted a way to model the charge density over space with different charges. And the charge density would essentially look like this for this, is that it would be pretty much nothing for most of the time, but then once you get to it, because electrons are pretty much point charges, you'd get a large spike, and then you'd continue. And in fact, this spike is undefined. It is undefined. There's a discontinuity here. And in fact, the Dirac delta function's definition is a piecewise function where, let's say this is, so x minus a, so we're just translating it because I've translated it. And let's call this point a. If x is equal to a, then this function, sorry, it's not equal to 1, but rather it is undefined for x is equal to a, but it is 0 otherwise, so when x is not a. And this is very strange, and there's one final property of the Dirac delta function, which is even stranger, which is absolutely pivotal to its usefulness. If you take the integral of the Dirac delta function over time, or rather over space in this case, overall space, you will get 1. It is a distribution, just like the Gaussian distribution or the normal distribution. And now, how can this be? And in fact, it gets even weirder. If I integrate over a period, which is a plus some tiny shift, some infinitesimal shift, epsilon, right? And I go on this tiny little period that includes the peak, this will hold. The entirety of space does not matter. All of the Dirac delta function is held at the point A. And that is the reason why it equals 1, is when you integrate over this. Now this is highly unintuitive, right? As long as it includes the peak, the integral will always equal 1. It's a very unintuitive thing, and to abandon rigor in favor of intuition, let's imagine a situation in which this happens. Let's imagine a box, right? A box function. Or a rectangular pulse, rather. And this rectangular pulse, let's imagine it has a width of 1, right? And we want the area under this box to be equal to 1. So we know that the height has to be equal to 1. But now, what if we were to squish this box, right? So that it was 1/10 its original size. Well, in order to be 1/10 its original size and still have area equal to 1, we would have to have a height of 10. And in fact, I can make this 100 and this will become 100. Right? And I can just keep going, and I can take the limit to 1 over n, right? I will get a height of n. However, no matter what my value of n is, as long as I'm integrating over the box, right, I will get an area of 1, right? Because the rest is 0, it doesn't contribute. But as the limit, as n approaches infinity, right, this will get infinitely thin, and will reduce down to pretty much a point, and this will get infinitely tall. In other words, we'll have a function which only exists at a point and is undefined at that point, but has an integral equal to 1. Now, this isn't the most mathematically rigorous way of describing this or even discussing it, but I believe it is a very intuitive way to describe it. And one very interesting thing about the Dirac Delta function is let's take the Fourier transform of it. So let's the Fourier transform, which we write like this, the Fourier transform of t minus a this is equal to 0 for every value of t which is not a. So this integral will also be 0 for every value that is not a. And at a, remember, as long as it includes this, the integral will be 1, but this will be 0 at that point. So what essentially happens is we sample this, and we end up with e to the I minus I omega 0, right? And we end up with 1. We have a function equal to 1 in the frequency domain. This means that if we plot it, I'm going to use a capital D, right, of omega. This is the Dirac Delta function in the frequency domain. It contains all frequencies with uniform weight. Now, this is very strange, but it also makes sense. You would need to have infinite energy in order to produce a pulse like this, right? And you'd also need all of the frequencies. However, this is something that's actually very useful to us because we deal with systems, right? But we don't normally deal with them in the time domain because it gets a bit complicated, but we deal with them in the frequency domain. So we have an input of x of omega, let's say, x of omega, and we have an output y of omega. And we want to describe this system. I want to know what this system will do to x and give me at y, right? Well, we take the input of x and let's put in a Dirac Delta function. Let's put in an impulse. Well, what will happen is this essentially samples the energy response or the frequency response of our system, because the frequencies which are amplified will get amplified and the frequencies which are dampened will get dampened, and we'll essentially get the frequency response. We'll get a print of the frequency response of our function, where we would have something that might look like this, right? Or something that might look like this. What this tells us is just by putting in an impulse, we have a direct print of the schematics of our system, of the energy spread of our system, which frequencies are let through and which frequencies aren't let through. Because if I put in a frequency at which the energy is quite small, my system won't really let it through. That will not exist at the output. So this is called the impulse response, or denoted by an h sub I. And it can be converted into time, but it's normally talked about in the frequency domain. And we have that if we multiply the input times the impulse response, we end up with the output. However, in the time domain, things get a bit more complicated, where we have to perform what is called convolution, which is essentially a combining of shapes, but that we're not going to discuss that in this video.